Okay, section 3.6, the chain rule and inverse functions. What I think the teacher wants you to do here is to kind of show or prove or derive that the derivative of ln of x is 1 over x. So if we know that e to the ln of x equals x, and we take the derivative of both sides, okay, this is what we get. And we're going to use the chain rule. The derivative of e to the ln of x is e to the ln of x, and then the derivative of ln of x, which is what we're trying to find, and that should equal 1, because the derivative with respect to x of x is 1. Then we will divide both sides by this e to ln of x, so we find out that the derivative of the natural log of x is 1 over, notice those are inverse functions, 1 over x. So we will get to use that, but we would be able to differentiate it if we needed to. Right, let's use that to solve this. The derivative of f with respect to t in this case, it's the ln of some x, right? Right there. So first it's 1 over the x times the derivative of that inside, which is 2t. So it's 2t over t squared plus 1. Now it says, note, it may be to your advantage to simplify before differentiating a function involving n. This function, ln of e to the 7x, right? ln, natural log, and e are inverse functions. This actually equals 7x. So the derivative of t with respect to, the derivative of f, this really should be with respect to t, is 7, right? If we do it the other way, if we say, okay, if f of t, or say natural log of e, we're going to call it 7t. So the derivative of f with respect to t, using our chain rule, the derivative of this ln, natural log of this x, is 1 over this x, right? Times the derivative of the inside, which is e to the 7t, times the derivative of that top piece, which is 7. And we get the same answer, don't we? So, watch and see if you can simplify before you differentiate. Alright, we have this special formula, and we're going to try to use it to show the same thing, that the derivative of ln of x equals 1 over x. So it's saying the derivative of this inverse function is equal to a composition function, the derivative of the original function with an input of the inverse. It's kind of crazy. So let's try this. We're going to say, if we're saying the inverse function is natural log of x, okay, we want to say that the derivative d dx of the natural log of x should equal 1 over the original function, which was e to the x, right, of the inverse, ln of x. Well, e and ln are inverse functions, so it should be 1 over x. We can use that here, okay? But we are going to use it in some future slides here. So, if I write this up here, we're going to say the inverse derivative of x equals 1 over a composition function where we take the inverse of x, and that's the input for the original function's derivative. Okay. Actually, I don't think we're going to use that here. We're going to use something else instead. We want to try to derive this arc sine. So if y equals the arc sine of x. Now arc sine and sine are inverse functions, right? So if I take the sine of both sides, well, these two are inverse and you end up just with x. So we are going to do a little implicit differentiation, right? We're going to take the derivative with respect to x on both sides. So the derivative of sine is cosine of y times dy dx equals 1. So we're going to divide both sides by cosine of y. So dy dx equals 1 over cosine of y. Well, keep in mind here, we're going to go back to a Pythagorean identity we used that said the sine squared, we'll use y in this case, plus cosine squared y equals 1. So let's solve this for cosine. All right? So cosine squared y equals 1 minus sine squared y. Then we'll take the square root of both sides. Cosine y is equal to the 1 minus sine squared y. Well, over here, we actually have, that sine squared, gotta get to it. We actually have that sine squared y is equal to x, right? So cosine of y is equal to 1 minus x squared, which is how we get 1 over square root of 1 minus x squared. So that's dx of the arc sine. Or another way to write it is the sine inverse of x. Okay, so we can derive that if we need to. Just got to keep in mind this good old Pythagorean identity. We could do the same things here if we needed to. Just follow the example on the other page. Now it says find the derivative of this. So we know this right here. Here we go. So here's the x, isn't it? So the derivative of f with respect to t is 1 over 1 plus the x, or the, in this case, squared, times the derivative of the inside, which is 3. Well, let's simplify this denominator. If we FOIL 3t minus 4, 3t minus 4, we get 9t squared minus 12t minus 12t minus 24t plus 16. So that is 3 over 9t squared minus 24t plus 17. Okay, so keep in mind what the x is when we're doing this. It goes right into there, but don't forget the chain rule. Okay, this one's interesting. We want to find the derivative. What we're finding here is the inverse function, the derivative of it at 3. And we can only use the data in the table. So what we need to know, quite frankly, is what's the inverse function of 3? Well, because f inverse and f, right, we can go and look at the original function and say, where does the original function equal 3? So we find that when x is 9, when x is 9, f of x equals 3. Well, take the inverse function of both sides. I can do anything to an inequality as long as I take the inverse function, as long as I do it to both sides. So the inverse function of the function, they drop out, and we get 9 equals the inverse function of 3. That's what we needed in this denominator, didn't we? So now it's 1 over f prime of 3. So when x is 3, f prime I'm sorry, not 3, 9. This should be 9, shouldn't it? Right there, because this is f, the original, or I'm sorry, the inverse function of 3, it's 9. So 1 over f prime at 9 is 5. So the derivative of the inverse function of 3 is 1/5. It's a little crazy, but that's okay. We're going to use this here. We're going to say, if we want to know the inverse function derivative at this, it's going to be 1 over the derivative of the original function times the value of the inverse function at this 4023, right? Well, we have to look at the original function now. If f of 2 equals 1423, and I take the inverse function of both sides, those cancel out, I find out that the inverse function at 4023 equals 2, doesn't it? So this becomes 1 over the derivative of the original function at 2, which they actually give to us, which is 1 over negative, which is 8 times 10 to the negative 4. Pretty sure. I have this in my notes somewhere. Alright, so what is that exactly telling us? Yeah, this is negative 8 times 10 to the negative 4. Well, look at the original function. The original function is the f of p equals g, where the input is p and the output is g. Well, the inverse function has to use the input of g to get an output of p. So the inverse function should be interpreted as the price in dollars when G gallons are sold. See how you can see that they're inverses. Well, what is this derivative of that inverse function mean? It means that, right, now it's the rate of change of the price, isn't it? So it's the rate of change of the price when G equals 1423. So the price is going down 8 times 10 to the negative 4th dollars when 4023 gallons are sold. Remember, these rates of change are instantaneous, aren't they? Instantaneous. Okay? Well, that's the end of this. I think the hardest part of this section is this crazy equation here and trying to use it. So maybe look for another example to try here. Okay? All right.